Welcome to the Machines and Molecules podcast. Machines and Molecules hosts guests with backgrounds in biotechnology, biochemistry, machine learning, and startups. And I'm Ingmar, your host. And our guest today is Victor Guallar, who is a professor at the Barcelona Supercomputing Center and the CSO and co-founder of Nostrum Biodiscovery. We'll talk in the category knowledge today because I'm going to pick Victor's brain on Monte Carlo simulations for protein discovery and optimization. I'm particularly excited about this because I did my PhD on Monte Carlo, but for Bayesian inference, which has nothing to do with molecules. So I'm going to learn a lot today. Hi, Victor. Nice to have you on the podcast.
Thank you, Ingmar, and thank you very much for having me in the podcast. I hope I can address some of these Monte Carlo questions.
How are you doing today?
Good, sunny and a little bit colder. It's a nice fall day, yeah.
Not as cold as it is in Berlin, though, I guess. So maybe for a start, can you explain what computer simulations of proteins and other molecules are and what they are used for?
So I think it can be easily understood. I mean, we are living in a world where simulations are a day-to-day basis of most of industries. We see when we design a house, we see a simulation of the house. When we are designing aeroplanes, we do simulations. So the same thing happens with when we go to the tiny space, and probably even with more reason, because we cannot look at atoms and molecules and have a visual inspection of those. We know that that's not possible because these are such a tiny sizes that our wavelengths are basically the same order of magnitude. So therefore, we can only get indirect measures of how they move, how they behave. And in that field, then it becomes more important that we can make models with computers. So imagine we have a molecule and we are asking this molecule how it behaves, how it moves, how we can get an ensemble of conformations. And with this ensemble of conformations, we can get observables. So that happens, and answering your questions, in pretty much all the fields of biotechnology or biomedicine. So drug discovery will be clearly one big example. Enzyme engineering for catalysis purposes, but also a lot of material science. So pretty much any technique, biotechnological technique, now deals with molecular simulations.
Mm-hmm. You used the term, and I'm trying to get as much terminology cleared out for as broad an audience as possible. You used the term that's called observable. When I came into a group at FU Berlin that did molecular dynamics, I was like, what do you mean observable? Can you explain the term? What does it mean? What is an observable of an atom or of a molecule or several molecules moving in space and interacting?
Yeah, well, probably it was a little bit too technical reference, but observable will be any property, biophysical or property that we can measure. In a sense, because we are doing models and we are always not sure whether these models will be realistic enough or will work enough, we want to correlate the results obtained from our model and even train. We probably can go more in detail how we might train these things at a later stage. But at least we want to correlate the results with experimentable properties. Let's say we measure changes of viscosity, changes of density, things that we can observe with a signal in an experiment in a lab. And then we have those signals for different molecules, for different contexts. We might change temperatures, we might change pressures. And then if our model can really predict those, then we can imagine that's a working model. We have this retrospective analysis, and then when we validate it retrospectively, we can use it prospectively, which is the most interesting thing.
Mm-hmm. So in other words, for example, you simulate a system of molecules moving and interacting in space, and from that system that you're simulating, you are calculating the viscosity of it, and you have actual measurements of the viscosity to which you then correlate it and see whether your simulation is any good.
Yeah, because in experiments you will see a signal, you will see a peak in a spectrum, you will see different coloring. Okay, this guy is colored, and as a scientist, what we want to do is understand, if possible, the relation between the molecule, the structure that we have, because let's remember we have structures from X-ray, for example, but structure is just a single photo of the picture. We need to see how it moves. So in trying to infer function from that structure, being able to generate these dynamical models and how those can predict and retrospectively correlate with experiments will give us confidence in that sense.
Mm-hmm. And so, as I said, I did Monte Carlo in my PhD. Then later on, I joined a group for my postdoc, which did molecular dynamics, which seemed like it was almost the same thing, but it was somehow different as well. And then at some point, I concluded, early on, okay, maybe Monte Carlo is good for anything but molecules. But now you use Monte Carlo to simulate molecules. So can you explain the difference between Monte Carlo and molecular dynamics?
Shame on you that you went into the dark side of molecular dynamics, the easy side. So it happened to me. Actually, it happened to me pretty much what you're saying. I did my PhD and I had really high theoretical aspects using Monte Carlo, and then starting looking at molecular dynamics and exactly saying that Monte Carlo was not that much used for large molecules. Maybe we first, so people can understand what's the difference between them. Let's imagine a molecule. We have a molecule because we have a structure from X-ray, etc. And that's, again, it's like a picture. It's a static picture of the system. And now let's say that you do some random change in that molecule. So computers can get us random numbers. That will be open a different discussion. And then with this random number, let's say we increase one distance or we move one atom in that particular direction. That's a stochastic random process. And then we interrogate whether the final state after this perturbation, after this change, is acceptable or not by looking at the energy of the system. Is the energy has get that energy more stable? Fine, I accept it. Opposed to that, molecular dynamics, we have the same initial representation of the system, but now we compute the forces. Let's say that because this atom is in the vicinity of all the other atoms, and in this particular context, it will experience a force. And that force dictates the direction that it wants to move. So once we have this force, we just apply a very, very small displacement to that atom, and then we recalculate the forces to that atom and to all the others. We recalculate the forces, another small displacement. So molecular dynamics is deterministic. You can always reproduce it, etc. And Monte Carlo is a stochastic. So different ways of moving things. So going back to what we were saying, I was very intrigued why Monte Carlo was not, because I love the concept of Monte Carlo. I don't know, it's kind of theoretical concept that was really intriguing me, and I wanted to be able to apply Monte Carlo to large molecules. And then we created this pellet technology that we can talk later on, and it does really allow you to move things in a more concerted way and to be able to apply it not only to large systems, but to, in our experience, obtain much faster results, a much more complete sampling results. So it not only can be applied, but you typically get better results in some particular cases. Of course, this is a source of a large debate in here.
Yeah. So what you're saying is that you're using kind of normal, what's called proposal distributions in Markov chain Monte Carlo, normal proposal distributions to displace atoms that maybe do not even have anything to do with the force field that's acting on the real physical atoms, and then accept or reject this, as opposed to forward simulating a differential equation that has been discretized. Okay, all right.
And now the key question is how you propose these moves, these random moves, these perturbations. And of course, if you do them at completely random without any logical, or let's say rationalization, any sort of algorithm that tries to map what we call the important sampling, the important regions. If you do them completely random at will, you would wait years until you accept something and something makes sense. But if you make those move in a smart way, you can really get a lot out of it.
And what is the smart, like, can you go a bit into an idea of what could be smart ways to update this?
So what we did in the past as a smart way, and probably going in the future now, people will frame it. So young people are listening to us. Here, there's a lot of room to code some AI smart way of doing Monte Carlo. That could be a great idea for next versions. But what we did is we use a lot of experimental information. So when we do a traditional Monte Carlo analysis of a system, we do millions, hundreds of millions of small moves in a very fast way. So each move will take fractions of a second, fractions of a millisecond, and then you will need to accumulate millions because it's very difficult to move all the system. You're doing the small motions. Instead of that, we said, okay, let's not do millions, let's do thousands, but each move will have a lot of knowledge coming from different sources. For example, we know that the proteins move in a sort of normal mode. We know that there are collective motion of proteins that we can address beforehand just from the structure or from some very early simulation. And those are the typical motion of the system. So we can now induce these displacements in, for example, all the carbon alphas of the protein or specific atoms of the protein that will be following these normal modes. And then I also know, because I have all these structures of proteins in the PDB data bank, that this particular amino acid of this protein likes to adopt this 25, 30, 100, 200 positions, but always is in one of these positions. So after I apply this motion, this random motion that I perturb the system, maybe I can resample those side chains and tell me which one of these 200 you like to adopt. So this kind of combining pre-existing knowledge and experimental knowledge into the Monte Carlo step, that brought us to take each Monte Carlo step maybe 1 minute, half a minute to 1 minute. But after the Monte Carlo step, all the system had moved in a concerted manner. Yeah. Of course, then the purist Monte Carlo people say, well, this breaks detail balance. There's a lot of biophysical implications on those, and it has to be fully reversible, etc. But we have shown that this heuristic Monte Carlo works really well.
Okay, so what you're saying is detailed balance is not necessarily there, but heuristically it works super.
And we have shown that detail balance, we recover detail balance to 90+%. So it's not that it's not there. We are almost there, and we can make fully detail balance simulation. It just takes a little bit longer, but we get the same results whether we follow 100% detail balance or we are 80% detail balance. We recover exactly the same solution. So.
Yeah, so because I was nerding out a bit here for the audience, detailed balance basically is a condition that allows you to mathematically prove that the simulation is correct in the sense of it's simulating from the correct distribution of the molecular system in this particular case. Very interesting. We talked a lot about simulations. Maybe can you explain a bit the difference between the simulation sampling from a distribution and optimization for people that come from deep learning, which is all the rage for some time now, and most of the time they know about optimization, but they don't know so much about sampling and simulation. So what's the difference between the two?
So there are many differences, but also to compare people who are coming on from an AI world, I would say that we are generating the data by doing this sampling. We do data generation. I mean, what people are doing now, and we are doing that as well. I mean, AI is here to stay, and it's actually helping us a lot, and it's a great thing. But that is more a data training. I like to explain to my students that AI is a complex linear regression, very sophisticated linear regression, but it's nothing beyond that level of problem simplicity. And instead of that, the simulations are creating this data. You get an initial state, and because you're solving these equations, you're generating tons of data. And what is now the hot topic, and we are applying it in pretty much all the cases in all the fields that are studied in my lab or even in the company in the real industrial applications, is using this virtual data that we generate with these biophysical techniques, Monte Carlo, molecular dynamics, even if it's the dark side, sometimes we enter the dark side, it's necessary to go in there. So whichever technique you use, you can generate all this virtual data. So new data. And now with this data, we do the optimization, we generate or we pass all these to some neural network that will create models based on this data that's not experimentally validated, but because we know for sure that there is a signal on the data, because we know for sure that while these molecular modeling techniques have false positives, they have a lot of true positives, and you get an enrichment factor. When you pass these things to AI, now you can generate very quickly new data. You can validate it again with molecular modeling, and at the end, you are having this recurrent enrichment that ends up in a very large enrichment factor of your results that you're predicting being true, being very good results. So, yeah, I would say it's about not analyzing the data, but creating new data, but both worlds synergistically give us the best results.
Yes. Maybe one side remark, and we'll cut that out, and I'll write it down. Your camera was a bit shaking 2 seconds ago.
Sorry, I guess my knee. I am touching the computer with my knee.
No problem. Just wanted to say it because I recorded earlier episodes and didn't say one thing the whole time, and then the guest was a bit unhappy right after. So generating new data, you say, so maybe in that sense, it's similar to what DeepMind did when it was training reinforcement learning algorithms on computer games and on physics simulations of robots walking in a system that had gravity, right?
Exactly. Now we are entering the era of virtual data. I mean, you don't need real data anymore. You can simulate data by other means, and as far as this data has some percentage of true positiveness, then you can make AI to enrich this and just become better.
There's this whole trend, actually. I was quite surprised that now at all of the machine learning conferences, suddenly people talk about molecular dynamics and Monte Carlo and so on and so forth again. I never expected this. Have you seen this coming, that machine learning adopts this?
So I gave a talk in a conference that AstraZeneca organized in London this June. I don't remember the title, but I think I said AI, a new life for molecular modeling, or a second life for molecular modeling. And it's true because who says molecular modeling can also apply for bioinformatical techniques, more traditional alternative techniques to AI that can give an alternative solution to the problem that AI is facing. And by giving this validation or second solution or second opinion, now you can combine them both and make AI to learn better, because we know AI has a what we call the applicability domain wall. So typically predictions are very good when they are close to your training data, but they become worse when you move away from your training data. And that's the main problem of AI. So if you have a second opinion for those predictions that are far away from your training data, but that there is some good prediction in there, then the AI will be, oh, okay, well, I was wrong here, but here I'm seeming to do well. So let's reinforce this. Let's actively teach AI. So I think it's not a trend; it's a reality. I would say that, for example, because of this, the drug virtual screening, how we can, given a target, search for new drugs, that's a solved problem. I mean, that problem that was one of the main problems 10 years ago, because of this capacity, and of course, because of having huge molecular libraries, that problem is gone.
Yeah. So you would say collecting a lot of experimental data so that you have a large data set of drug candidates that you have screened against so and so many receptors, probably that's not necessary because we can simulate in these cases.
Yeah.
Right?
And for example, you can use generative modeling from AI, that the same one that we see creating with DALI new images and new things. So that can create molecules, lots of molecules. And then the molecular modeling will tell, oh, these are good, these are bad. And then pass this information to AI. And then let's do it again. Those cycles can be happening in very few hours. And in very few days, you can have a huge list of very well-designed molecules with very good synthetic properties, etc., to your particular target that before it took you 1 year. And now you have it in days.
Yeah. That's a very interesting viewpoint. There's whole startups that are built upon the hypothesis that you need all that training data because machine learning can mostly interpolate but not extrapolate. But what you're saying here is, well, just amend machine learning with simulation and suddenly you close this gap as well, also with computers. That's very interesting.
Data will always be welcome. Certainly. It will facilitate the job. As much data as we have, perfect.
Yeah.
It doesn't hurt.
Yeah, absolutely. So you're a professor and you are a founder. How do you split your time between the two, and what motivates you in these two worlds?
That probably is more a question for my wife. How can she allow me to do this? But and my son, well, because I like it a lot, of course, and I just put more hours, and there's no secret in them. Also, the two jobs are highly related, so I think I got a good equilibrium because the company is a spin-off of the research center, so the center is also very interested that the company goes well. It brings revenue to the center, and the problems that interest us are the same in both. I mean, of course, the company has to be applied, has to be connecting with real industry, and the center can do more crazy things. But we are both rowing in a very similar direction. And also because I have a bunch of postdocs which are amazing and they do a lot of work. So yeah, you need to delegate. You need to trust the people under you and delegate. It's the only solution.
Yeah. Was the company your first foray into the industrial world, or did you work in industry before that?
I didn't work in industry myself. I collaborated with industry before. So I had some studies with companies, pharmaceutical companies, and naive studies, I would say, where I was looking at everything from a very academic perspective, thinking that what we had was great, was going to solve. And then you realize, well, maybe it's good, no? It can help, but industry is much more complex than all these things. But certainly because of this initial context, I saw that we could, that our software, that these Monte Carlo simulations could bring some solution into these problems that they were facing. So yeah, without that, I don't think I would have probably jumped into this experience. Yeah.
What would you say have you learned from the industry work, and how does it change maybe also your research agenda?
It has changed completely my research agenda. It clearly showed me that a lot of the research that's done at the universities and each country is different, but in general is highly disconnected from what the industry needs. Even though they think it's connected, it's not that connected. And in that sense, now, of course, I love to do things that have nothing to do with industry, and there's a lot of scientific work that I still do, or my lab does, completely disconnected from industry. But then I find a nice pleasure, and that was one of the main motivations when I changed subjects from my PhD to my postdoctoral degree, that I wanted all these hours that I was putting in the lab to have some meaning, to be worth of something. So I have a very good pleasure when I see that this actually works and that it can solve a problem, and that gives you a very nice reward for all the time that you're putting in there. So having that connection is at least in my case. Other people might be more just focused on solving the equation. I find a lot of reward when that can be applied.
Yeah, I understand that. I also found when going to industry, to a research team in industry, that just having the application in mind clearly shapes also your prioritization of what you're working on, and your whole thinking around whether whether you can make an impact with that. Whereas before, it's mostly, oh, I'm interested in this. It's a nice puzzle, so I'm going to work on it. And in general, like thirst for knowledge, I think, is a big motivation for many researchers. But I also thought that if you connect this to some end goal, it can be very rewarding, at least if, there's no boss with a leash that's telling you to go this direction or that direction. It's a very nice place to be in. And luckily, we live in a time when science has become a mode of work in industry as well.
Yeah.
So the theme of the podcast is that the guest brings a third M word apart from machines and molecules. Have you thought of a third M word?
Yeah. The M word I chose was multidisciplinarity, which is something that has that impacted me when I was young, and that has driven a little bit the way I learn or the way I try to do multiple things. And if you want, I can explain you why.
Yes, please go ahead.
I think I was a teenager. I don't remember how much, maybe 10, 12 years or 13. And I saw this TV show about Miguel Servet. Miguel Servet was this scientist from his Spanish scientist that discovered the blood circulation system. And this guy, so Renaissance, he goes into Europe, early Renaissance, he goes into Europe, and he studied in I think in Belgium at the and then he was good at everything. He was good at math, at medicine. He was, of course, at that time you had to be a theologist, but he played music. He was good at architecture. He was an amazing painter. And I was, wow. I was, honestly, that TV show, like, it really shocked my ground. I was like, I want to be this. I want to be this. And then I really believe that that's the key of creativity. The real key for being able to, of course, you're going to be focusing. I focus in biophysics, and I love them, and that spends 70% of my time. But then you need to do other things that at the end will be more beneficial for your work, and expand as much as you can, and try to excel in many other areas.
So it's not just multidisciplinarity inside a research group, but also on a personal level.
Personal level, yes.
Okay. And so do you paint then?
I don't paint. I'm horrible at painting. But I do other things, yeah. But painting is one that I am really bad at. And I try, but I'm not good at.
What are you particularly excited about apart from research?
Well, I do music, I do gardening, I do a lot of sports. I wanted to be a professional basketball player. I mean, that was when I was young, that was all I wanted to be. And I was very, very depressed when I didn't succeed in that. But, door closes, another opens. And that, for example, that shows you discipline. So that discipline then can be really applied at the lab. And all these really things that try many different things, and those will only enhance your productivity to the final professional field that you developed in.
That's very interesting that you say you wanted to be a basketball player and that didn't work. So that was around the age of 18 or 16, 17?
Pretty much, yes.
Okay. Yeah, it's very interesting. Max Welling, who was a guest in this podcast before, he told us about the story that he wanted to be a fighter jet pilot, which was completely surprising to me. Also didn't work. And then yeah, he said everything was poured into research at a later point in time.
Science was my third choice, but at the end is the one that I end up with.
Yeah, I understand. I also had other things that that I wanted to do earlier on, and I agree with you. It rounds you up as a person if you have walked down a few avenues.
Mm.
Like one thing, I think that is in resonance with what you say. One thing that I realized is that some of the path I have chosen, I've just not walked long enough, and I saw friends who continued on the path, and now they get some recognition also, and well, depends on what. So the artists, they still have a hard time making a living from it, even though they get recognition. But in other parts, it seems to be, well, stick with it for long enough to really make an impact rather than giving up early. And that seems
doing it with multidisciplinarity. Don't put all the eggs in one basket. Try to do multiple things.
At least to keep your sanity, right?
Yeah.
Yes, I think that's a good advice to give. Thank you, Victor. It was very enjoyable to learn about how Monte Carlo can actually be used for molecular simulations, and to hear about your other adventures. I hope to see you at some conference soonish, and wish you a great weekend.
I hope so too. And Ingmar, thanks very much for having me in the podcast.
Thank you. Bye-bye.